The Moon is the only natural satellite of Earth and its closest neighbor in space. According to the most widely accepted theory, it formed after a Mars-sized object collided with our planet. This ancient catastrophe, which occurred billions of years ago, melted Earth and hurled a huge amount of debris into space. That debris eventually cooled, took on a spherical shape, and became the Moon. Today, this crater-covered body orbits our planet and is responsible for tides in the oceans. The Moon's diameter is a little more than 1/4 that of Earth, making it the fifth largest natural satellite in the solar system. The Moon goes through several phases: new moon, full moon, first and last quarter, crescent. But no matter its phase, it is difficult to confuse it with any other object in the night sky, and sometimes even during the day. Now imagine waking up at night and noticing that the familiar disk looks different, larger and brighter. In your half-asleep state, you might not realize that you are actually looking not at the Moon, but at Mercury. The surface of the planet closest to the Sun resembles the lunar landscape. It is also covered with numerous meteorite craters. Mercury's size is about 2/5 that of Earth, slightly larger than the Moon, which means its influence on Earth would be stronger. Nights would be brighter and tides more intense. Its lunar cycle would be around 14 hours shorter, though overall, replacing the Moon with Mercury wouldn't drastically affect our planet. But what if Venus, the third brightest object in the sky after the Sun and Moon, took the Moon's place? Venus is often called Earth's sister because the two planets are similar in mass and size. Seen from Earth, Venus would appear enormous, comparable in size to the view of Earth from the Moon as captured by Apollo astronauts. The morning star would shine 6 times brighter than the Moon and cover an area of the sky 16 times larger, making the nights glow like early twilight. Blurred, swirling patterns in its yellowish-white cloud cover would be visible. However, Venus likely wouldn't become Earth's satellite instead. The two planets would orbit a shared center of mass, creating an unstable orbital configuration. If Venus moved at the Moon's orbital speed, a collision would be unavoidable. Let's continue the thought experiment. If Mars replaced the Moon, you would immediately notice its reddish glow and a disk twice the size of the lunar one. A telescope wouldn't be necessary. You could see dark markings on its surface with the naked eye. And even if you didn't notice the changes visually, you would certainly feel their consequences. Mars is far more massive than the Moon, and its gravity would disrupt the delicate balance of Earth's tides. Anyone near the coast when this replacement occurred would need to evacuate quickly, as massive tsunami-like waves would crash onto the shore. Mars reflects more sunlight, so nights would become brighter and landscapes would take on a reddish tint. Through a telescope, you could even observe Olympus Mons, the tallest mountain in the solar system. Although Mars isn't large enough to drastically alter Earth's orbit, over time, Earth and Mars might become a dual-planet system, orbiting a common center of mass. Under such conditions, traveling to Mars would seem far more feasible. Now imagine an even more drastic substitution: Jupiter taking the Moon's place. Earth would no longer be an independent planet, but would become a satellite of the giant. Yet the sky would be breathtaking. An enormous striped sphere, dwarfing the Moon many times over, would stretch across the entire horizon. You would see endless yellow, brown, red, and white cloud bands of Jupiter. If you managed to enjoy the sight of Jupiter's floating atmospheric clouds, it wouldn't last long. The gas giant's immense gravity would almost immediately trigger earthquakes, volcanic eruptions, and colossal tsunamis on Earth. The crust and mantle would begin shifting toward Jupiter, and the planet would eventually be torn apart. Earth would be stretched and compressed by tens of meters. Unfortunately, Earth's orbital speed is only about 10% of what is needed to maintain orbit around Jupiter, so within less than a day, Earth would collide with the giant. But let's consider a less catastrophic case. If Saturn replaced the Moon, the view would be spectacular. This massive planet is more than 35 times larger than the Moon. Its golden disk would span roughly 18 degrees of the sky, and its famous rings would stretch from horizon to horizon. Earth would orbit slightly farther out than Saturn's moon Dione, and due to Saturn's immense mass, Earth would quickly become its satellite. However, Earth's orbital velocity wouldn't be sufficient to remain stable, and after a few days, it would inevitably crash into Saturn. Before the collision, Earth would have to pass through Saturn's rings, composed of fragments of comets, asteroids, and shattered moons, a dangerous journey. Additionally, navigating among Saturn's 53 moons would be extremely challenging. If, by some miracle, Earth avoided collision and became Saturn's 54th moon, the giant's strong gravitational pull would create intense tectonic stress, tearing Earth's crust apart. Ultimately, the planet would not survive. Uranus and Neptune are ice giants of roughly the same size, larger than Earth but smaller than Saturn and Jupiter. Their surfaces are hidden beneath icy layers and tinted bluish and greenish-grey. If either of these planets replaced the Moon, the consequences would be similar. Let's assume Neptune takes the Moon's place. Imagine looking up at the sky one day and seeing a huge bright blue sphere, Neptune, a planet 14 times larger than the Moon. It would be visible both day and night. Its disk would seem nearly 15 times larger than the Sun's. Solar eclipses would become a regular occurrence. Whenever the Sun slipped behind Neptune, Earth would be plunged into darkness for about an hour and a half. Since Neptune's mass is 17 times greater than Earth's, our planet would inevitably become its satellite, orbiting slightly farther out than its largest moon, Triton. In such a scenario, Earth might eventually collide with Triton. But let's imagine we are incredibly lucky and no collision occurs. Even then, we would face enormous problems. Tides would become 1,000 times stronger and seismic activity would constantly increase, triggering massive earthquakes and volcanic eruptions. Earth wouldn't be torn apart, but it would heat up significantly. We might even lose internet access. The infrastructure simply wouldn't survive. Now picture two parallel horizontal lines. Connect them in two ways, with a vertical line and with a diagonal one. Which is shorter? Of course, the vertical line. It's the shortest path between the upper and lower lines. The same principle applies to reaching orbit. The simplest and fastest way is to go straight up. The lower line represents Earth's surface. Our planet is an enormous mass of matter, nearly 6 sextillion tons, or 6,000 billion billions. This immense mass acts as a powerful magnet, helping, among other things, to hold the atmosphere in place. The upper line is the boundary of that atmosphere. Everything above the top of the atmosphere is orbital space and the vast openness beyond it. But the atmosphere itself is made of matter, a mixture of gases with density. When a shuttle launches, all this air presses against it, creates drag, and significantly slows its ascent. You can imagine movement in a vacuum as slicing through air, whereas climbing through the atmosphere is more like forcing your way through a thick jelly-like substance, such as grape or strawberry gelatin. Enormous energy is required to push through this medium, and all the while the craft is fighting Earth's powerful gravitational magnet. Airplanes, unlike rockets, use atmospheric density to their advantage. It helps them lift off the ground and stay airborne. This is possible thanks to two factors: engine thrust and wing shape. Wings split the incoming airflow into upper and lower streams. Both streams seek to rejoin behind the wing, but the wing's shape forces the upper airflow to move faster. Faster air becomes less dense, so the air beneath the wing becomes relatively denser, generating lift. Essentially, wings allow an aircraft to glide through the air. But to take off, a plane needs substantial thrust to reach the required speed. That required speed varies greatly by aircraft type. Small planes need roughly 96.5 km/h, while large airliners require around 241 km/h. For example, a Boeing 747 uses nearly 3 tons of fuel just to take off and climb to an altitude of 3 kilometers. These numbers sound impressive until you compare them to the needs of a space shuttle. The first thing you notice about the shuttle is its small, stubby wings. They would be completely useless for a horizontal takeoff. On the other hand, large wings are unnecessary in space, and building them strong enough to withstand launch forces would be extremely difficult. This is why the shuttle's wings serve only one purpose: ensuring a safe landing so the craft can be reused. Their size is enough only to keep the shuttle stable during re-entry, preventing uncontrollable spinning and allowing a guided descent without active engines. The shuttle's engines are fundamentally different from airplane engines. Aircraft engines require air from the atmosphere, but the shuttle cannot rely on that. There is no air in space. This is why it uses rocket engines. To understand how they work, simply inflate a balloon and let it go. It will fly in the direction opposite to the escaping air. This is the basic principle of rocket thrust. For a rocket to launch, it needs an enormous amount of thrust and a tremendous supply of fuel. A shuttle could not manage this with only its three main engines, which is why it requires two additional solid fuel boosters and a massive external tank that is jettisoned near the end of ascent. Only the combination of all these components provides the necessary power. The total thrust produced by the three engines and two boosters is about 3.5 million kilograms of force. The external tank holds roughly 725,000 kilograms of rocket fuel, and to control the flight, the engines must have an extraordinarily complex design. Could the shuttle reach orbit if it were redesigned to use the atmosphere the way airplanes do? Unfortunately, no. Maintaining the required speed while climbing along a diagonal trajectory would demand even more fuel. Even if an aircraft managed to reach the upper layers of the atmosphere, Earth's gravity would still hold it firmly in place. To leave the atmosphere and enter orbit, any object launching from Earth must reach escape velocity, the speed at which gravity can no longer restrain it. For Earth, the required orbital speed is about 28,000 km/h. This is far above the speed of sound and many times faster than the cruising speed of a commercial airliner. Imagine an airplane capable of flying that fast. How much fuel would it need, and how strong would it have to be to survive such forces? The cost and engineering complexity would be completely unrealistic. Realizing that traditional shuttles may eventually become obsolete has pushed scientists and engineers to explore alternative methods of reaching space. One proposal is the construction of a gigantic space elevator. The idea involves building an enormous tower reaching up to a satellite in geostationary orbit, which moves in sync with Earth's rotation. Such a structure would need to be about 35,400 kilometers tall and made from an extremely strong material, such as carbon nanotubes. A platform inside the tower would travel using electromagnetic propulsion, allowing passengers to reach space in just 5 hours. This megastructure would make space travel faster and safer. However, existing carbon nanotubes are not yet strong enough for such a tower, so the search for a suitable material continues. Another concept with a similar approach is the space tram. It would require a vertical vacuum tunnel in which a shuttle could accelerate through magnetic levitation. With no air, there would be no drag, and electromagnetic forces would propel the craft until it reached a velocity close to escape speed. Such a shuttle could be lighter because it wouldn't need to carry an enormous amount of fuel. But a major problem remains unresolved. Could humans withstand such extreme acceleration? Otherwise, the crew might not survive the journey. If these ideas sound strange to you, that's perfectly understandable. But there is yet another possibility: using airplanes to launch spacecraft. No, an airplane cannot reach space on its own, but it can serve as an excellent launch platform. The plan is to build a special aircraft with a wingspan of about 122 meters, capable of climbing above 10 kilometers. A small shuttle released from such an altitude would not need to pass through the denser parts of the atmosphere, making it much easier for it to reach orbit. Richard Branson is already developing this approach through the Virgin Galactic program, aiming to take tourists to the edge of space.